Welcome to Super Easy Physics and Mathematics. Today we're going to be looking at the solution to IGCSE Physics, Paper 2, Extended Variant 1, May-June 2024. I'm Orisheje Matthew. So let's go into the paper and see what we need to do. The paper is for the duration of 45 minutes. And then you are expected to answer 40 questions. But this video is going to be in two parts. I'm going to take the first 20 questions, question 1 to 20 in this particular video. And then you can now go to the second video to look at question 21 to 40, which is the part 2. The main constant we are going to use, acceleration due to gravity, for this particular test is going to be 9.8 meters per second square. The total mark for this paper is 40 mark. So let's look at the question quickly as we walk through it. Question 1 is on vector and scalar quantity. So let's just quickly look at what the question is all about. So we have two rows here. Say categorize this quantity into scalar and vector quantity. So we have the first one here, mass and energy. So if we have this is scalar and then this is also scalar, then weight is vector, acceleration is vector. So the first answer here is A. Okay. Now, if we look at some other vector quantity that are given here, you have vector quantity momentum. So we have momentum. Then we have velocity. And we have force, and we also have gravitational field strength. Exactly. So we have gravitational field strength, which is another vector quantity. So let me look at the thickness of this pen I'm using. It's quite big, so let me reduce it. Okay, now so let's go to question 2. Which name is given to the quantity of matter in an object? So that is definition. It is mass. Density is mass per unit volume. So this is mass per unit volume, that is density. Volume is the space occupied. Then weight is the gravitational attraction on an object. So the weight of an object, the mass multiplied by that. So quickly, let's go. The SI unit of mass. What is the SI unit of mass? The SI unit of mass is kilogram. So we'll just see how we can quickly do some review around the topic that are given to us. So let's look at question number 3. A body is moved from place X to place Y where the gravitational field strength is different. What happened to its mass and what happened to its weight? Now this question is just testing the differences between mass and weight. You know that mass is universally constant. It's universal constant. What do we mean by that? The mass of an object on Earth is the same mass that object is going to have in Jupiter, on the moon, or in any other planet. Then, but the weight of an object vary from place to place. So weight is the gravitational attraction of the planet on an object on it. So weight vary from place to place because the value of G also varies. So this value of G, as the gravitational field strength varies, so it varies from place to place, and so the actual answer for this one is that what happened to its mass and then to its weight due to the move. The mass remained the same while the weight varies from place to place. So the mass remained the same and then the weight varies. So the answer is C. Then question number 5. The mass of an object is 2.5 kilogram. The volume of the object is 480 centimeter cube. So we want to know what is the density of the object. So for us to find the density is equal to mass divided by volume, but they must be in the same unit. So this one is centimeter, so in gram, so we must convert that to kilogram. So that will give me 2,500 gram, then divided by 480 centimeter cube. The reason is that all the units given here is gram per cm. So you make sure that it's consistent. And if you do that, this is going to give 5.208 gram per cm cube. So the actual answer there is going to be B. So that's for number 4, is B. So let's go to the next question quickly. Question number 5. 4 objects have 2 forces acting on them. Which object is in equilibrium? So which of them will be stationary because of the force acting on them? So this is A. So the force going due east balanced with the force going due west. So this is going to cause rotation. So this is coplanar force. So this object is going to rotate, and then this object is going to push to the right, and then this object is going to move towards the left. So the only one that will be stationary is A. So we look at question number 6. A ball of mass m falls vertically and it strikes a hard surface. Its speed on striking the surface is v1. So you have an object. This is the object, so let's call it this. This is a ball as it's been described. Okay, it falls down, and then the speed downward is v1, and then on striking the surface it rebounds upward with the speed v2. Now remember that the velocity is a vector quantity. So if it's going up, v is going to be negative, and then when it's coming down, v is positive. So we can now calculate what is the difference in the momentum. So momentum coming down is mv, mv1. The momentum going up, take it away from the momentum going up, which is what? mv2. So if you open the bracket, you can now have, this is called the impulse, so which is the difference in momentum. So this will be, so the answer, if you open this bracket, is going to give us mv1 plus mv2. So the answer here is C. A stone is dropped from a tall tower and fall a distance of 50 meters to the ground. The stone has a mass of 5 kg. What speed does the stone use to strike the ground? So in this case, when the stone is going to drop, okay, so let me just explain this at this part here. So this question 7, look, I can do this explanation up here. So we have the stone before it drops, okay, at a height above the ground. Okay, so we have the ground here, and then this stone is at this height above the ground, okay, which is given there as 50 meter. And then this stone right up here, it has potential energy, and then as it falls down, the speed is going to increase, and it's be converted to, the potential energy is converted to kinetic energy. So right at the bottom, so we have the kinetic energy, so half mv square, and then right at the top we have the potential energy as mgh. So since the total potential energy is converted to kinetic energy, so you can now say that mgh is equal to mv square over 2. So in this very particular motion, you say is the same object, so the mass has no effect. So if you drop an object of 10 kg and you drop an object of 2 kg from the same height, they are going to fall with the same, strike the ground with the same speed. So consequently, make V subject of formula, so V is equal to the square root of 2gh. So substituting, we can do that to get square root of 2 times 9.8 times 50. So that will give the speed. So that speed is going to be, for that is 31.3 meter per second. So the answer is B. All right, so let's make progress as we go to question number 8. So I will have to be a bit faster so that you can spend a less time reviewing this question. Coal-fired power station generate electricity. Coal is burned and the energy release is used to boil water. The steam from the water make the generator move. So when generator move, this is kinetic energy, okay, and then this produces electricity. Which rule give the name of the energy stored in the coal? So coal, okay. Okay, so this is chemical energy stored in the coal that will be burnt and then to release, and then so I think you have chemical and kinetic energy. So question 9, okay, a man put some ice cube in the water. So we have ice here, and then put it on the water, and then it's on top of warm water, and then the ice is going to melt and become water. Okay, so what happened here, this process is called this is melting, ice becoming water at the melting point. And then what happened next is after some time it condenses, okay, so and then all right, I think there is condensation. It's not going in that direction, rather is going to be, all right, Ctrl Z. Okay, so we have air particle condensed to water, so this is condensation, yeah. Okay, So you have melting, ice turned to water, then air turned to water. So they say what is taking place here. So that is going to be condensation and melting. So correctly. Okay. A gas of volume 200 cm cube is trapped inside a cylinder by the piston. So this is the piston here. So the volume is high. And then the piston is pushed to the right. So if you push it to the right, and the volume of the gas decreases to 100. So push this piston here to this point. Alright, so we have the piston move to this point. Okay, so the entire gas has, okay, oh, this is giving me something I don't want yet. Alright, so let's assume this. So if it doesn't want to move, so let's just do the shielding. Alright, so the volume here, so you have, this is V2, and then the entire volume here, so we can call this V1, and then this is V2, and then the pressure here is P1, and then the pressure here is P2, and then we know that, well, Boyle's law, inversely proportional to the volume. And so if you have that, so you have this little graph here. Okay, so right here we have which one do I put here now? Okay, so let's say here is the volume of the gas, and then right here is the pressure, okay, of the gas. So we started with okay, 200, then the volume was reduced to 100. Then what is the nature of the relationship here? It reduces. Alright, this is going to be like this. Okay, that is a graph. So at this point, so we can do this, trace it up here. Okay, right, and then it goes this way to this point here. So this is P1 and this is V1, and then it's reduced down to this point. So you have this. So when the pressure was increased, so, and then this is V2, volume decreases. So what happened here is we're trying to look at the relationship between, okay, so if we have this, quickly, so let's do this. Alright, so we have P1 V1 equals to P2 V2. Alright, so we are looking for P2. So P2, okay, is equal to P1 V1 divided by V2. So this is equal to P1, okay, times 200 divided by 100. So if you look at that, so this go into this to give me 2. So consequently, we have P2 is equal to 2 P1. So the volume doubles, Force per unit area doubles. Okay. 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 Now, you say what is going to happen to the kinetic energy? It's a function of the temperature, and then the temperature remain constant. So this is the answer is C. Okay. What number is that? So number 10 is C. All right. Please just quickly subscribe, comment. I want to listen to you. Like and share this video, and then that is a way you can actually help what I'm doing here to contribute to your academic success. Okay. All right, so let's see let's move to the next question quickly. The next question is question 11. So question 11. All right, so you can see everything. Okay, so now, which graph show the relationship between pressure and volume of a fixed mass of gas at constant temperature? So this one is actually related to question number 10, which is Boyle's law. So the answer is D. I've actually explained that, so let's just don't waste time here. Okay. But another way that this graph can be done, had it been, they said this would have been correct if this is the reciprocal of the volume. So if you have this as 1 over V, not the volume itself, so pressure as, so if we plot it, because we know that pressure is inversely proportional to volume. So if you are plotting the pressure against the reciprocal of the volume, it will give you a straight line, which is a direct relationship. Okay. So let's look at question 12. What is question 12? It said during the evaporation of a liquid, the most energetic particle escape, and then the temperature of the remaining liquid varies. So let's look at try to give you a pictorial view so you can understand what happened during evaporation. So you have a container, and then we're going to put some, so we have this container, and then this is the surface. Then inside this container you have some particle. Okay, so we have water, and then this water. So let's assume this is the total particles that are inside the water, and each of them, so this one is more energetic, so it's going to have the energy of this, the energy is 3 joule. So this is 2 joule, this is 2 joule, this is 2 joule, this is 2 joule, this is 2 joule. So what is the total energy of the system? So we have 1, 2, 3, 4, 5, which is 10, plus this is 13 joule. Okay. And then because this is close to the surface, so this one can break away and it escape to the surface here with, okay, the 3 joule escape, so it's no longer there, so we can remove this. Okay, so if that escape, what is going to, so you take away this, so minus 3 joule, so the total energy remaining is 10 joule. So what happened? The total kinetic energy of the system have reduced, so the average kinetic, the velocity of this molecule remaining is going to drop. So the average kinetic energy is going to drop, and because of that average kinetic energy going down is going to lead to decrease in temperature, which is the cooling effect. So it causes decrease in temperature. So this increase in temperature is what is accountable for the cooling effect of evaporation. So cooling effect of evaporation. So what all right, sorry, is effect, not effect. See it. Okay, right. So which role identify where the particle escape from and then describe the temperature variation. So you look at that, the particle that escape, so which place it escape from the surface, so it's going to be either C or D. So then what is going to happen to the temperature? The temperature will decrease. So this one, temperature decrease. So these two correct. So the correct answer is C. Okay. So let's go to the next question, which is question. A wet clothes are put out on a line to allow the water in the clothes to evaporate. Okay, which type of weather causes the water to evaporate most quickly? So we are looking at the factors affecting the rate of evaporation. So what are those factors? So quickly, let's just review. So you have one, the presence of wind. Okay. Then temperature, which is a higher temperature, rate of evaporation increases with temperature, that is hot weather. Okay. And then we also talk about the humidity of the surrounding, humidity, the amount of water present in the surrounding. Then we also talk about the surface area exposed, the surface area exposure. So these are major factors that affect that. If you have this, so on which type of weather will increase, so you have here, we're actually looking at what? Hot day with wind. So the answer is D. So we have wind and then temperature. So hot day with wind, that is question 13. So let's go to okay, question 14 has been delisted because the question was defective. So let's look at question 15. A solar water heater is designed to absorb heat energy from sunlight. Which surface texture and color will be the best for the solar water heater? So what we have done now, we are looking at what is the major issue here is absorption. So we want the device. Oh, sorry, what did I was writing water. Okay, so we want absorption of heat. Okay, so what will it do? So what is the major thing that will make the panel to absorb? So we have what? Black surface. Black surface are better absorbers of heat. And then you have dull surface or matte. Okay, so what do you call it again? If the surface is a dull surface, okay. All right. Okay, dull surfaces are also good absorber and emitter of heat, but shiny surfaces, these are good reflector. So this one does not encourage absorption. So any of these two, so it's going to be dull black. Number 15, so the answer is dull black surface. Number 16, which statement about wave is correct? Okay, for number 16, wave transfer energy without moving the particle. So the particle just bump up and down. So if you look at maybe this water wave, you have something like this. So you see maybe you have a bottle, the thing bump up and down while the wave is traveling to the right. So this is just definition question. So those definition questions, you know the definition, pick it and go to the next question. So the angle of incidence of light on a plane mirror is gradually increased, so to the nearest degree. What is the maximum possible angle? So if we do this, so let's have a plane mirror at this point. So let's have a plane mirror here. Okay, so if this is a plane mirror, so this back is the coated part, and then the front is the shining surface. So let's have a ray of light come. So if we have this, so first of all, we have this, the normal. Okay, then we have a ray of light incident on it. Incident, yeah, cool. Okay, right. Oh, I'm not getting this now. Okay, so do this, and then it will also be reflected in the other way. Cool. So this is incident ray, the reflected ray. So the angle of incident I, then the angle of refraction R. So what is be the maximum? So the best you can have is this 180 combined together. So the answer is 180. Okay. Okay, which conditions are necessary for light to be totally reflected? Okay, angle totally reflected. So one, this is D. So let me show you this. So we'll talk about total internal reflection. The first condition is that so let's have the interface, and then below on the interface, so we can have here. Okay, so let's have water and then air. So then let's have the normal at this point, and then the ray of light for total internal reflection to take place. The ray of light must travel from, so let's okay, let me do this. So the ray of light must be traveling from the more dense medium, okay, to traveling from the most dense medium, traveling towards the less dense medium, and then at a critical angle, which is C, then the ray is going to travel, the refracted ray will move between the interface, and then the angle here is going to be 90 degrees. So at this point, so what are we saying? The angle of incident for total internal reflection to take place okay, so we have this one. What conditions are necessary for light to be totally reflected? to be totally internally reflected. So for total internal reflection to take place, so we will have this now. You have a blue ray, the angle of incidence of the blue ray is greater than the critical angle. So if you have a ray that comes from this point greater than critical angle, and then the ray goes back again into the medium, so in this case we say it is totally reflected. So what is the condition here is that the incident light is in the more dense medium, so which is in water, and then the angle of incident is greater than the critical angle. So the angle of incident, which is the blue ray, so that is I, so it's greater than the critical angle. So let's go to question 19. So this one had to do with calculation of refractive index, Snell's law. So this is Snell's law to find refractive index n. So it's equal to the sine of the angle of incidence in the less dense medium to the sine of the angle of refraction in the more dense medium, transparent substance. So that will give us sine. The angle must be measured from the normal, sine 40. This is a direct question over sine 30. Okay, so if you do that, so that is going to give us about, I think it's just 1.2. Okay, 1.29. So the answer is B. All right, so let's look at optical fiber. Okay, this question on optical fiber. The diagram shows light in an optical fiber. Now for light to move in the optical fiber, the correct answer here is D. Okay, now the glass must slow the light as much as possible to make the critical angle for the fiber as small as possible, so that the light can remain totally reflected within the optical fiber. Now let me just explain, give you some bit of information about the optical fiber. So you have two layers. We have the clanging material, so which is the outside one. So this one is a less dense material. So we have this as a less dense material, two layers. So that is a blue. Then within the inner one, so let's have this. So this is the more dense medium. So this is the more dense medium. So the refractive index of this is N2. Then the refractive index of this is N1. So N2 is greater than N1. So we can have a ray of light. So a ray of light that is coming as is shown here. So it comes, okay, from the point and all right, sorry. Okay, incident at this point. Okay, and then it's reflected back into the medium because the angle of incident is greater than the critical angle. So this one is greater than the critical angle, and then it's reflected back. So this refraction keep going on inside this, and then goes, and then goes, and then the signal is transmitted within the object because this one is less dense and then this one is more dense. So now for it to, what we are trying to say that this material here must have a higher refractive index to slow down the light because it's moving in a more dense medium. So light slow down. When the light will travel faster in medium 1, than in medium 2, which is in the core of the optical fiber. So it slows it down because of the high refractive index. And then the critical angle of the fiber must fall enough so that to keep it within. So the relationship between the critical angle and then the refractive index, you know, critical angle is equal to arc sine of the refractive index. So we have that. So we give you critical angle, or refractive index is equal to 1 over sine C. So basically this is all about the first part. I think we just put and this one here because time, so that when you are going through the video it will not be too heavy for you to preview. Okay, quickly. So while I would have thought maybe I should just answer the question 21 and this. Okay, well, let's just answer this question 21 and 22. And then so we have the region of the electromagnetic spectrum used to detect fake banknotes. Oh right, fake banknote is C, ultra. Okay, then a sound wave travel at 300, so V is 330 meter per second. The distance between the center of a compression and then the center of the nearest rarefaction is in the sound wave is 2.5 cm. Okay, so look at this one. We have this. So we have compression, 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 rarefaction, rarefaction, rarefaction. Then you have compression, compression. Okay, then you have rarefaction, rarefaction, rarefaction. So compression to compression is wavelength. Then compression to rarefaction is half wavelength. Okay, so what they told you now is what? Lambda over 2 is equal to 2.5. So lambda is equal to 5 cm. So now this is meter per second. So we convert this to meter, which is equal to 0.05 meter. So we can now find what is the frequency. Frequency is equal to velocity over wavelength. So that is equal to 330 divided by 0.05. So if you divide that, question 21, so if you divide that, that is going to give you C. Okay, so just do that. So you have your calculator. You have 330 divided by 0.05. Okay, that gives you 6,600 Hz. Okay, 6,600 Hz exactly, or 6,600 Hz. Okay, that is great. All right, so I think we just put a pause on part 1. So I will encourage you, subscribe to Super Easy Physics and Mathematics. I will be very, very happy to see your comments. Like and share the video with your classmates. All right, and then with this, you can scan this barcode here to have, if you want to contact me, and then this is my WhatsApp group. So you can join the WhatsApp group and then let's continue the learning. All right, so because I'm trying to be posting questions maybe at regular interval to review some questions. So the questions I asked here, we can actually discuss them on the WhatsApp group. All right, so keep learning, keep making progress. My desire is that your grade will improve. So stay tuned and remain blessed.